This is Jim Hedershot, ready for lecture number 33. This particular lecture is dedicated to considering the thermal situation of electric machines. We're going to talk about the sources of heat and where it goes and what can be done with it. Then we'll have another lecture after this one on some cooling strategies. The importance of thermal analysis of electric machines can't be overemphasized, and the modeling or monitoring of the temperature condition while it's operating. If you take control and of the cooling of the machine, you can increase the torque and power density. You can prevent magnet demagnetization. You can maximize installation life and identify even pending rotor and stator failures, and you can make sure that your motors comply with agency limits and that they don't exceed agency thermal limits. The options for cooling electric machines are listed here. You can have natural convection on the frame. By natural convection, that gives you the lowest torque density, and then you get some cooling effect from the mounting conduction of the motor and the frame to the surface it's mounted to, and sometimes that's significant in certain machines. Some applications, there are even fins provided on the mounting flange for the machine, for the motor, to aid in cooling, and because you get radiation cooling from these, not just convection, but you get radiation cooling from the frame and the brackets. Then there's forced air cooling, either internal or external. Then finally there's internal liquid cooling. There's a wide variety of fans that are used that are either mounted inside the motor, in between the bearings, right on the shaft to circulate air inside of there, or suck air. These are centrifugal fans to suck air through an end bell and out past the end turns of the conductors on the rotor, and blow finally onto the end turns of the stator. And there's two kinds of blades you see here. The bidirectional one, that one goes either direction, is the least efficient and it's the most noisy, but it'll give you the same cooling in both directions. The one on the right here is unidirectional, but it's quiet and quite efficient. Anytime you study the thermal conditions of an electric machine, it's good to have in mind what the thermal conductivity constants are for all the common materials, in particular the ones that they're used in a motor. So we have a list here that we've compiled, and these are in watts per meter Kelvin, and this includes all of the materials used in a motor. I think it includes them all. Hope we didn't miss one. Plus it includes some other materials for reference that aren't used in a motor. I think there's a couple there. So you see there's a wide variation. It's interesting to note that the best thermal conductive materials on this list, of course, is copper, and aluminum is a close second. But look at the ones that are terrible. Air is awful, but fortunately it's a gas and you use a lot of it, so that's why it can be effective cooling medium. Even though it's static air, it's not a good thermal conductor. It's almost, you call it an insulator. But then water's not that great either. We use water cooling, but it's not that great of a thermal conductor for static water either. Ceramics are pretty good. Oils aren't that great. Varnish is very poor. Epoxies that are filled with aluminum nitride are pretty decent. Epoxies filled with titanium nitride are pretty good. Epoxies filled with boron nitride are quite good. Now powder coating, epoxy powder coatings used for stator cores, that we saw in some earlier lectures, those aren't bad, but they're sure not great. Now here's the bad ones. The varnish that's used, the varnish isn't listed here, but the varnish that's used on the magnet wire is the same kind of a number that for fiberglass, Nomax and Mylar. Nomax and Mylar are the slot liner materials. And you see that is very poor. So the main source of heat's in the copper, and it's got to get through these insulators. And now the powder coat's quite a bit better than Mylar or Nomax, but still not that great. So these slow up the conduction of the heat generated. Fiberglass is not that great. Magnetic stainless steel, so-so. Non-magnetic stainless steel, Hyperco 50. This is a lamination material. Silicon steel, cold rolled steel, iron. It's all getting better and better. The metallics are certainly better than the plastics or the hydrocarbon materials. So it's good to have those in mind. Varnish. Oh, the varnish is here. Varnish is the same as the enamel that's on the magnet wire itself. It's not very good either. Some of them are filled with some solids, which kicks them up a bit. That helps a lot. In some of the earlier slides, I discussed several times the ventilation plates that are used in cores to provide cooling passages. And here's some nice close-up pictures of some of these. Here's a ventilation plates used on a rotor of a motor, probably an induction machine. And here's a segmented plate for a synchronous generator with open slots. Here's a stator vent plate. Here's another segmented stator plate, and here's a generator vent plate. Obviously, this one only goes one direction of rotation, and there's some pumping action here. But this is a stator core. I'm not sure why they're angled like that. But what these consist of is a fairly thin piece of steel with stand-ups on it. These are all various shapes and contortions of these. See, even this spreads the stator teeth apart. These little stand-up blades, and these are usually stamped, formed, and welded in jigs. And they use some of them are handmade, some are automated, semi-automated. So these are, you don't find these in small machines, but I think more and more you're going to see that in the future. This is an example of a large rotor for an induction rotor, and it has these vent plates on it, and it's got fans, paddle, or I don't know what kind of a fan you call that, but and I don't completely understand the cooling theory behind this. It looks like those fan blades are, I'm not sure what they're for. I don't see how that cools the rotor or the stator, but certainly these cooling vents in here in the stator and rotor core shorten the thermal diffusion paths. That's their purpose. And here's some of the circuits that you see that are generated from these paths. Here's your stator, and there's your rotor, and the ventilation passageways are lined up between the rotor and the stator. So somehow with a fan, a shaft-mounted fan, you get the air to blow in here and come out the vents and be collected and circulate. This is external air going through a heat exchanger. These are used in these big power plant generators, or no, I'm not thinking of power, I mean wind turbine generators. Yeah, you'll have an external fan that will blow in here, and it go through this heat exchanger, and then the forced air that's forced through the vent ducts goes through this heat. Sometimes this is actually hydrogen or nitrogen that's pumped through here, and then it's cooled through this heat exchanger with outside air. This is a 10 kilowatt machine with a liquid cooling jacket around the outside. There's your inlets. This is interesting. This will have an inlet on this end and an outlet on that end, and it'll have another inlet on it'll have another inlet, but it'll be on the opposite end. So you have two inlets, one on each end. So because there's a temperature rise or a delta from as it takes the heat out, it gets hotter. So you get a more uniform gradient across the stator if you have two inlets, one on opposite ends and two outlets. Now here's a case of a big high torque density machine with an external blower on it that I don't know if that's blowing or sucking. I believe it's sucking because there's the filter system. You want to filter that air, so this sucks air in there and blows it through the machine, and it vents out both sides of this end of the end belt, so that forces it out the end. The only thing about this, you have to keep this filter clean, so there has to be some kind of a temperature sensor or an airflow sensor, something in here that tells the controller or some maintenance people when the filters are dirty, because if those get blocked, you're going to cavitate and you won't get the proper cooling, the motor overheat. Here's another example of that. Here's a blower motor that blows air through the motor. Here's another example of a servo motor with a quite a large blower motor that's blowing it through it, and it ventilates out the end belt on each end just like that one. Now here's an example of a very large machine with hydrogen coolers, stator core, field windings, bearings, rotor, high voltage bushings, and retaining rings, axial fans, brush holders, collector rings, stator winding, stator end ring support. This is probably this collector rings. This looks like a synchronous generator, stator cooling water system, seal oil system, hydrogen cooling system. Serious cooling required on big machines with long diffusion paths to get the heat out from the sources. Here's a picture of a stator that's been encapsulated to improve the thermal conductivity from the sources. It's insulated through these slot liners because the heat from the copper's got to get in the iron, which has got to get in this jacket out here. And this jacket, these jackets are usually two-piece, and they have spiral grooves in the OD, just like what we saw in this machine here. We don't see the spiral grooves, but they're in there. And so this is a water-cooled stator core, all right. But if you leave these end turns sticking in there, their only path for heat rejection is through this air, stagnant air, unless there's a fan on it. But even then, the thermal conductivity of the air is so bad that it's not going to be very effective. So what they did, they completely encapsulated this whole motor in a ceramic material which has a pretty high thermal conductivity. It's a thermally conductive material with fillers in it. Now to look at a lump parameter model of a motor, you can think of it in terms of the sources of heat and all the nodes. And here's a description of and different materials, what they're made out of. So each one of these has a different thermal conductivity. Aluminum, steel plate, pure copper windings in the stator, cast iron frame, end windings, and all these things. So these are the issues and how complicated it is to predict the temperature. You can build a lump parameter network like this using a bunch of nodes and treating all these as resistors and solving this circuit with a source and predict with the characteristics of all the materials. You can predict the temperature rise. This is a software product that comes from England. It's called MotorCAD, and this is developed by a very smart guy, and it's used to predict the temperature rise in machines. This thing's kind of out of place, but the service life of insulation systems degrades big time with increase in temperature. It's long been said and agreed upon, accepted that for every 10 degrees in temperature rise, you shorten the life by a half. So here's an example of a winding and what happens to its service life. At 100 degrees C, it's got a 114-year life. At 140 degrees C, it's got a 6.8-year life. So that should be up in the slides in a different place. But the machine thermal condition, of course, determines how you can operate the motor. Here's our traditional torque speed curve with the continuous operating range and the thermally limited range. So this is a time-dependent operating range. So you can oversize the machine and get higher continuous performance. But the other thing to do is to improve the thermal capacity and the thermal rejection of the machine by using the right materials and allowing the machine to run hotter. You can do that. Like, for example, if you're limited by magnet temperature, you can use higher performance magnets that, like rare earth magnets, are doped with dysprosium to increase the temperature capabilities. There's one company, Electron Energy Corporation in Pennsylvania, under a contract with the Air Force, have developed rare earth magnets that operate successfully in operating temperatures of 550 degrees C. But all these things you have to consider: heat versus cost versus weight versus performance versus volume. The thermal resistance of electric machine is a very important parameter that's used, and most motor manufacturers will manufacturers that have catalog machines, I mean, that you apply from application methods and order the motor to suffice your need. I'm not talking about special machines like used in the auto industry for traction motors. They don't have to publish these kind of specs. But if you're going to buy somebody's motor, they're trying to entice you to buy it, then you want to know what its thermal resistance is, because if you whatever the watts are that it takes to produce the power that you need, you want to know what the thermal resistance is for what's the degree C per watt temperature rise you're going to get. So this allows you to predict the temperature at different loads and helps you determine how long you can stay at different loads, or whether you have to back the load down to cool off for a while. So the temperature rise equals the total watts of losses at any given load, any given current, times this thermal resistance. And usually manufacturers will give you two numbers. They'll give you a number in the winding and a number for the surface of the frame. Now because you can affect the one at the surface of the frame a bit by external cooling and by mounting, but it's pretty hard to affect the one in the winding unless the machine is built for an external blower, blow air through it, or you got liquid cooling. The highest temperature in the machine is usually in the end turns of the phase windings. And you can look at a NEMA spec ICS 16, and these are the guidelines for measuring the thermal resistance of machines. There's different methods it's done. It was probably first done by Electrocraft, by Erland Persson and his engineers, and they measured the thermal resistance of small machines, size 23, 2¼ inch brush type motors, and 3¼ inch and 4-inch motors. And the way they measured thermal resistance is they mounted the motor to a 9-inch square, 1/4 inch thick aluminum plate, and they hung it up from the ceiling in wires, and then they locked the shaft, and they applied, they fitted the windings and the surface with thermocouples, and they monitored the temperature with a data acquisition system as they applied a certain watts to the machine. They used DC. They tied all they went across two phases, two leads of the 3-phase motor, so they could have a circuit, and they would put DC on there and measure the current and voltage, and they knew what the watts were, and they'd watch the temperature rise. And they keep increasing this until the temperature stabilized, so it wouldn't rise anymore. So they knew that was and then would calculate the degrees C per watt thermal resistance from the machine that way. It doesn't matter if the losses are iron or copper. They measured them as all copper, but it's certainly applicable to iron and copper and windage and everything. So remember, the motor constant versus the motor constant was the rate of torque divided by the square root of the watts. So what one should do is plot the motor constant versus the thermal constant, and then you can, if you do this, then you ought to be able to, if you using this parabolic curve, you ought to be able to estimate what the thermal constant is for any motor that you're designing. You still have to measure, but this is a good indication of a start. And the other thing you could do, if you have a lot of motors in your company, you should make these measurements to develop your own history, and you could compare that with a rotor surface area and volume. This is a thermal model of an AC induction machine that was presented by Dr. Kylander. It's the same idea as Dave Staton's, but you can build a solver for this and calculate this. The problem with these kinds of lump parameter thermal models is that there's so many variables that you don't know what to put in the circuit. You don't know what values to put in for these things, because the biggest problem is thermal transitions over one surface to another. For example, you've got a stator and you've got slot liners in it. Well, are the slot liners touching all the conductors? Are the slot liners touching the slot all the way around? No, never, and it varies from one machine to the other. So the ultimate temperature of the machine will be right, but the time scale of these different components of the machine won't be right. So that's the biggest problem with that. So you still have to take measurements of this. One time I had a contract from the Air Force, and we took a bunch of motors and that were constructed different ways, and we measured what the resistances were for the material transitions. We made measurements of that and tried to make a database that if you were going to use we had a lump parameter model design, and to use that, we would decide, well, how are we going to make this motor? And so we go in this table and look up the right resistance values for the material transitions, but you still don't know if the motor's made exactly the way you thought it was going to be made. You still have to measure it. So the I squared R losses vary with the winding temperature because of the change in resistivity of the windings, you see. So and there's so there's, as the winding heats up, the losses goes up because the resistance goes up. For example, the I squared R losses in a stator go up increase 40% with 100 degrees C rise in temperature. For aluminum, 100 degrees C rise increases 70%. So this is what's going on in the rotor of your induction motor. It's not as bad with copper, but it's bad enough. So then there's a big difference in performance due to the thermal characteristics of magnets, the B and the H. Here's a summary that I alluded to in a previous one, but you can see what the difference are. The flux drops 0.2% per degree C of temperature rise. The resistance to demagnetization actually gets better as you get hotter. The ferrite motors resist demagnetization better when they're hotter. They have a reverse coefficient, unlike other kind of magnets. But what that means, if a ceramic magnet is used in cold temperatures, it'll demag when it gets cold. That's why for automotive applications, for the 80 motors in every car, they use ceramic magnets for, I don't mean hybrid cars, but regular combustion-driven cars. they have to design their magnetic circuits to withstand, minus 40 degrees Fahrenheit. Now, samarium cobalt has the best thermal characteristics of any magnets ever made. The remnants drop is 0.03% per degree C versus neodymium, which is 0.11% per degree C. The coercivity, or the resistance to demagnetization, is also not bad with the samarium cobalt, 0.2% per degree C. With neodymium, it's terrible in the toilet, 0.6% per degree C. So you got to be very careful with demagging neo at elevated temperatures. But remember that as summarized here, the changes in B changes the torque and the voltage constants. They drop by that percentage. And so that gives you less torque and efficiency and power. Now the drop in H, that affects the demagnetization and the maximum current limits you could supply. So these are very important things to keep in mind. Here's a summary of the heat transfer parameters and their relationships. If you plan to build your own lump parameter model and do some thermal analysis, this is some of the data you need to have to do that. So that concludes this lecture. Thank you very much.